fantastic application of the cloud, leverages the fact that all of our resources are connected to the internet with rich security controls in place, but also rich capabilities for sharing and opening up access to your data, to your machine images, and other AWS-hosted resources. And so very early on, we saw a pattern that was developed with NASA and with several of our academic partners to create collaborative research environments in the cloud. And what I mean by this is an environment where you're treating the cloud as a neutral environment, a Switzerland, if you will, where researchers from many institutions, instead of having to negotiate firewall rules, having to figure out, okay, who's going to hold a copy of the data, or which institutions will have many copies of the data, how do we synchronize source code, do we ship source code and then recompile in all these environments and then run some tests to see if these are consistent. Instead of going through all of that hoopla, you instead have a common environment with shared machine images, shared containers, shared data sets in Amazon. And you have maybe subsets of your data that are selectively available to maybe individual members of the collaboration. Some of this is available to the world. We give you the tools and capabilities to create these collaborative research environments in a way that's both not only cost-effective, but more importantly, very accessible and secure for your collaboration. Citizen science applications, which we'll talk about too, have leveraged the scale and the global accessibility of Amazon's resources. So when you have projects like the Zooniverse and the Galaxy Zoo project that might one day start with just 10 users and then quickly grow to 100,000 visitors to their site, we can seamlessly handle, of course, the scale of the web infrastructure behind these applications and the databases and other technologies that are needed to support these types of applications. And then more importantly, make the research data products from these applications accessible in a broader context with other data products that combined bring more value to all of that data. And then finally, we have science as a service applications. And so by this, we mean those types of applications that abstract away all of the infrastructure and give the researcher the ability to just focus on the science. And maybe in the case of genomics, upload genomic data files and have a managed application handle alignment, variant calling, all of the processing of your genomic data so that you can then focus on identifying linkage between specific biomarkers and the diseases that are correlated with those and treatments that might prove effective with those specific disorders. So the value proposition that we see for scientific computing on Amazon really focuses in these areas. We help you. The cost savings are important to researchers, but far more important is the time to science benefits. The fact that we don't have queues. You don't have to wait minutes, hours, weeks, or even months to be able to get access to high performance computing or high throughput computing resource. Instead, these resources are available instantaneously. And this does two things. If you have a research project that you can predict needing infrastructure for some period of time down the road, we can get you the infrastructure just when you need it. But more importantly, when you have an idea as you're driving or riding the bus to your office in the morning, you have the infrastructure available instantaneously to take that thought experiment and turn that into a computational experiment, which then might translate into a much larger investigation. So effectively, we're allowing you to have access to science at the speed of thought instead of being constrained by availability of resources. And then, of course, the global accessibility and the security of the cloud are incredibly important. We'll talk about security especially as it relates to genomic applications. So why does Amazon care about scientific computing? It really bundles into three broad categories. One, to a person within Amazon. This is across all of Amazon.com. We love science. We love the outcomes of science. We want to make our world a better place. And if we can support and accelerate the pace of discovery, find cures for disease, help us better understand the impacts of climate change and potential mitigations, we can help better understand the origins of the universe, that excites us. That causes us to wake up and say, this is a great place to work. Secondly, this is a valid business model for Amazon. It's a profitable business for us. And so this means that it's sustainable in the long term for us to focus on scientific computing and invest in teams like mine and on the partnerships that we've formed. Thirdly, and this one's really interesting, the scientific community uniquely brings the types of requirements that you really can't find elsewhere. We'll talk about the Square Kilometer Array, for example, as a project that's really the biggest of big data projects out there. If we can meet the needs of projects that are working with zettabytes and publishing exabytes of data, we can meet the needs of our commercial customers for many years to come. And so by working with the scientific community, we feel that we're positioned to better serve all of our customers in the future. So I talk about a couple of programs that relate to the work that we're doing with scientific computing, one of which is our research grants program. And Amazon's offered a number of forms of grants, both for education and research over the years. The research grants program, and you can see the link to it on the slide, allows us to invest in capabilities that accelerate time to research and make access to computational and data-intensive algorithms, tools, data sets, and papers and resources. We help make these more accessible to the global research community. And so you can think of this as an applied research grant program where we're giving grants to organizations like the UC Berkeley AMP Lab, to the University of Washington, and to many researchers who are either proving that something's possible to the world, doing it for the first time, clearing a path for others to follow, or we're helping a researcher to take a well-understood workload that's been proven to be possible in the cloud and do a little bit more work to package that up and make it easy for researchers, thousands or hundreds of thousands of researchers around the world to then follow that path in a way that's going to reduce their risk, accelerate their time to science, and reduce the cost of using cloud resources for these types of workloads. So if you have an idea that you think would be well aligned with this project, would encourage you to take a look at the page and apply. The second thing that we've done to make scientific computing on AWS easier is focus on our partnerships with education and research networks around the world. And so today we have peering in place with every major academic and research network. You see a few of the major examples displayed on the slide here. And furthermore, we're now starting to waive egress fees for research workers, for research workloads that are data or computationally intensive. And the purpose of this is to make the cost of using AWS very predictable for the research community so that it's easier to write cloud resources into the grants that you're submitting. And so if you'd like more information on this program, I encourage you to reach out to your AWS account manager, and we can help you take advantage of cloud resources and simplify procurement of AWS. Maybe one more thing on the topic of research networks. In addition to having peering with the networks in the way that many institutions do, we've also now begun to build dedicated peering for specific projects. So the Large Hadron Collider at CERN, for example, generates a pretty sizable amount of data each year. And the Energy Sciences Network, ESNet, which is the Department of Energy's network, has partnered with Amazon and Pacific Northwest Gigapop to establish 100 gigabit peering through our US West 2 region in Oregon, all the way to CERN. So now the high energy physics community has access to all of Amazon's resources and the ability to easily transfer data back and forth at scale. Something else that our team focuses on is public policy. So great if you have the means to acquire Amazon, you figure out billing, we've simplified that, you have the network capacity. But it sometimes takes a little while for policy to catch up with the capabilities that the cloud offers. And one area that was a little bit murky, a little bit cloudy for researchers was genomics, especially human genomics applications. And so if you looked at the NIH policy around working with human genomic data in a cloud environment a year ago, the policy stated you can't have this type of data on computers that are connected to the internet. And so we've worked very closely with the NIH to say, is the VPC, is Amazon Virtual Private Cloud and VPNs and using IPsec encryption, is that the internet or is that something different? And so we worked very closely with the NIH and with a number of the institutions that the NIH funds to develop security best practices that show very clearly how one could safely and securely, and respecting patient privacy, store and analyze and access this data and collaborate on these types of human genomics applications in a cloud environment. And so a policy that was announced by the NIH director, Francis Collins, last week references this document that was co-authored by a couple of folks within Amazon that says, here is step-by-step how you could deploy these types of applications in the cloud. So if you're working with these types of workloads, please take a look at /genomics. Link to this paper is on the left-hand side of the page. And so I wanted to now shift a bit and focus on some specific ways that researchers are using AWS. So I've talked a little bit about CERN. So the Large Hadron Collider just came back online. It's been shut down for about a year and a half as they've been going through an upgrade to increase the energy of the accelerator so that you've got these protons accelerating and smashing in at higher and higher speeds. And also to increase the sensitivity of these large digital cameras, the particle detectors, CMS and ATLAS. And over this past year and a half, while the engineers were improving the physical instruments, we've been working with the ATLAS experiment, one of the biggest particle detectors at CERN, to help them determine how could we leverage AWS at scale, especially EC2 Spot, both to do simulation of what might happen when you have interactions of various types, and also to analyze the data of actual interactions to then be able to compare those results. And it's when you see a difference in what you predicted would happen versus what you observed that you get a Nobel Prize. And as you can imagine, when there's a hint that you're getting close to maybe understanding the Higgs boson or understanding dark matter, there's a race to be the first person to be able to analyze that data and show demonstrably how this actually works. And so when when a conference comes up or when these results are about to be published, there's massive need for computational resources. And so we've worked with the ATLAS experiment initially and now CMS to show that their infrastructure was capable of leveraging hundreds of thousands of cores concurrently using EC2 Spot, our available capacity that's not being used, to very cost effectively and very quickly run these simulations and analyze the data from the Large Hadron Collider. And so now that LHC is back online, we expect to see continued usage of AWS by both of the major experiments there. Another project that we're very excited about is the Square Kilometer Array. So the SKA is a radio astronomy project. This is the biggest of big data projects that I'm aware of. It has two phases. The first phase will create 2,500 linked radio telescopes across Western Australia and South Africa. The second phase will have 250,000 of these telescopes. The first phase will generate zettabytes of raw data, which will then be reduced to 3 to 5 exabytes annually of data that will then be published to the global astronomy community. And so we're working with the SKA to help develop the App Store for astronomy in the cloud. And so I would encourage you to pay attention to the SKA if you're interested in the field of astronomy or super big data, to see ways that you could get involved in helping to create that App Store and make it easier for astronomers to not only manage and work with data at this scale, but also to make it easier for astronomers to access data-intensive and computational techniques that maybe are a little bit harder than they should be today. A couple of examples of high-performance computing. We have automotive manufacturers that are running workloads that maybe many of you thought wouldn't be possible to run in the cloud. This is computational fluid dynamics, it's crash simulations. These are tightly coupled workloads that are being run in an ensemble approach. And by that we mean having smaller clusters that are each focusing on a portion of this simulation, working in a very tightly coupled fashion, but in aggregate having many clusters that are dividing up the larger simulation and then merging these results together. This has been a very successful approach, and we now see many, many members of the automotive community around the world that are sharing these techniques with each other and starting to standardize on this cloud-based approach. You may have heard about some of the very large-scale workloads that are being run, coordinated by cycle computing. A great example is the Schrödinger example of creating of analyzing and simulating compounds that might be the next best technology for solar panels and solar electricity generation. And so a researcher at USC simulated with molecular dynamics software running on EC2 Spot 205,000 organic compounds to find which would be potentially the best for photovoltaic cells. An amazing amount of work in that, 264 years of computation being completed in just 18 hours at a very, very reasonable cost for the types of results that they get. And then examples of science as a service applications. The genomics example that I was mentioning earlier, we have many instances of these types of applications running on Amazon. Globus Genomics, a longtime partner of ours, founded out of University of Chicago and Argonne National Lab. DNA Nexus, Seven Bridges Genomics. There's many players in this field that are making it very easy for clinicians and researchers to work with human genomic data in a safe and secure and private way on Amazon, and letting researchers focus on the science instead of the infrastructure. Similarly, the Weather Company, we have a link to their case study published below, using Amazon, continuing to use Amazon at scale to produce some of the world's most accurate weather forecasts and make these available to consumers and businesses around the world, running these simulations on Amazon in a constant basis using many of our high-performance computing instances. And then the last example I wanted to talk about is it's one that's near and dear to me, which is a project we did with Planetary Resources, an asteroid mining company in Bellevue, Washington, just outside of Seattle, and NASA Tournament Labs and the Catalina Sky Survey. So we onboarded a large repository of imagery, of observations of the night sky, the Catalina Sky Survey, as a new Amazon public data set. And we worked with NASA Tournament Labs to have developers create new machine learning algorithms that would run on top of Amazon EC2 to analyze this data, to come up with a better mechanism for determining these objects in the sky that are changing over time. Are these asteroids? Is it a satellite? Is it something else? And the result of this work is that there's now an algorithm, machine learning algorithm, that's 18% better at finding asteroids. And this video, which you won't be able to see the whole thing, shows just the pace at which new asteroids are being discovered. There's several 100,000 asteroids that are already known using the previous algorithms. We expect to find tens of thousands of new asteroids by going back through the entire Catalina Sky Survey with this new algorithm, and doing so at a very, very low cost. We expect to submit tens of thousands of new asteroids. Hopefully none of these are on their way, on their way towards Earth in a dangerous trajectory. If they are, we'll use the cloud to find that and come up with a plan. So at this point, I'd like to invite Mike Franklin to come up and talk about some of the work that's being done at the UC Berkeley AMP Lab. So thank you, Mike, for joining us today.
Okay, well, thank you, Jamie.
Yeah.
Great. Well, thanks for having me here. Yeah, what I want to do is tell you a little bit about what we've been doing at the AMP Lab across the Bay. Amazon Web Services has been one of our main sponsors and partners since the beginning of the lab, and so I'm happy to be here to be able to tell you a little bit about what we've been up to. So the AMP Lab is a collaboration in the computer science department at Berkeley. We've gotten some nice press about some of the impact we've been able to have. But the idea is it's a group of about 80 faculty, postdocs, graduate students, undergrads, and some staff that come from kind of the spectrum, across the spectrum of computer science. And so if you might know some of the faculty involved, but our expertise is in data management, in machine learning, in computer systems. We have some people who help with security, with human-computer interface, and so on. One of the interesting things about the way we set up the lab is we're about half funded from the federal government. So we were one of the projects that was announced when the Obama administration put together their big data research initiative back in 2012. And we also have 28 companies that we work with closely as industrial sponsors. Again, Amazon, being one of the leading ones. And what we're doing in the AMP Lab kind of dovetails well with some of the examples Jamie was just giving. The name AMP stands for Algorithms, Machines, and People. And the idea is that these are the three very different resources that you have available to make sense of big data. So algorithms, we think about machine learning, statistical inference, and so on. When we talk about machines, obviously we're thinking about cloud computing, large-scale cluster computing. So how do you do scale-out processing and elastic processing to make sense of big data? And then, just like we saw in the previous example in the citizen science domain, the idea of people here is really twofold. One is, of course, we want to support data scientists and analysts who are trying to make sense of data. But the other is you can think about crowds of people, whether expert or non-expert, as a resource. And in fact, we're heavy users of Amazon Mechanical Turk and other crowdsourcing platforms like that to actually get people out on the internet to help us collect data, to help us clean data, and even to help answer some of the questions or the parts of questions that the algorithms and the machines can't quite handle yet. And so the kind of the overall goal of the AMP Lab is to build the foundation and the infrastructure that can help you combine these three very different types of resources in the right proportions to solve whatever data analytics problem you're trying to solve. Okay, so that's at a high level what we're doing. More specifically, we've been releasing a lot of open source software. So we're building something called the Berkeley Data Analytics Stack. Some of you might have heard of it. It's abbreviated BDAS, and that acronym is pronounced badass. And probably the most famous thing we've built is, if I don't kill myself here, is this thing called Spark. It's now known as Apache Spark. And I'll tell you a little bit more about it, but it's a processing engine for doing scale-out computing. But if you look at what we've done, all the things in blue are things that we've built in our lab. They've all been open sourced. A couple of them haven't been quite released yet, but they'll be coming out before the summer. But if you go down to the bottom, we've got resource virtualization for taking large physical clusters and allowing people to treat them as individual virtual clusters. We do a lot of stuff at the storage level, not in actual file systems. In file systems, we use S3 and Hadoop file system. But we've got Tachyon, which is a caching layer built on top of those platforms. Succinct is a compression layer. We've got some work we're doing on encryption and so on. In the middle is Spark, which I'll tell you more about. And then above that, we have a bunch of different ways of processing data. So if you want to run SQL queries, we have a system called Spark SQL that lets you do that. If you want to run graph algorithms, GraphX is a way of doing that. Spark R lets you take programs written in the statistical language R and run those on a cluster using Spark. We have a streaming interface for real-time processing. And then we have over on your right a bunch of stuff for machine learning. So MLlib is a very popular distributed machine learning library. We have some tools built on top of that to make machine learning easier to use. And then Velox is a new system we're building for doing real-time machine learning. So we drive our work using a bunch of applications that I'm going to tell you about next. But the basic idea is that each one of these boxes is sort of one or two PhD theses. We're an academic lab. But our students are really committed to building usable, industrial strength open source software. And so each of these is being released as part of this overall system that we're doing. So a big part of what we do at AmpLab is community building around the badass stack. And so just some things that we do. We started about 3 years ago a meetup group for Spark in San Francisco. We had a few dozen people show up. There are now, as of last night, according to meetup.com, 57 meetup groups around the world in 21 different countries. We run something called the Spark Summit. We just had our first Spark Summit East in New York a few weeks ago. There'll be another one here in San Francisco in the summer, where people from the Spark community get together to talk about the future of Spark and what they're doing with it. And then the AMP Lab itself runs a bunch of things we call AMP Camp, which are tutorials for teaching people how to use the system. So part of what we do is the research and the software development, but we're also very active in building the community around it. In terms of applications, I'm just going to mention a couple of them. In order to figure out whether what we're building is actually going to be useful, we looked around campus and in some other universities for scientific applications and other applications to help us drive the research. In terms of genomics, we've built a genomics processing pipeline I'm going to tell you about a little later in the presentation, a system called ADAM. And ADAM was actually used recently by some collaborators at UC San Francisco to help diagnose a very rare disease that the young man in the picture had, where he had shown up at a hospital in Wisconsin. They couldn't figure out what was wrong with him. They took a sample of his brain fluid, sent it to our collaborators at UC San Francisco, and using our software and a bunch of other stuff that those people had developed, they were able to extract out sort of all the human DNA and RNA in the sample, look at what was left, and then diagnose what was wrong with this boy and help cure him. So, we use this as an example to show that, there's a lot of people interested in big data, for serving ads and for, doing all sorts of things. But if you can process this kind of information really quickly, you can have, a real impact on people's lives. So I'll tell you a little bit more about that. Another thing I'll just mention briefly is an application we built called Carrot, which basically runs on a cell phone, watches what applications you're running and what's happening to the battery with when those applications are running, and then collects all that information into the cloud, and then builds models of how different applications use the battery on different phones with different operating systems. And what that lets you do is, for any individual user, these reports get uploaded to the cloud. They get a report back that says, hey, we noticed that with your phone, whenever you run, this certain application, your battery drains really quickly, and we can tell from looking at other examples that if you stopped running that application, your battery would last an extra, hour and 27 minutes a day, right? Or we could say, hey, whenever you run this map application, your battery drains really fast. Other people that have your phone don't have that problem, so maybe you need to uninstall it and reinstall it because something's wrong there. And the reason I like to show this example is because it's sort of the classic example of big data and why it's important. Because if you do this type of analysis on a couple dozen phones, you don't see anything. There's no useful information there. But if you can start to get more and more information, and in our case, we've had almost 1 million downloads of this application now, that's when you can start to see these greater patterns. Okay, so you can see patterns across the whole population, and then you can use what you find in those patterns to then make very specific recommendations back to people about what they should be doing. And it's maybe a little glib, but you don't have to think too hard to look at this pattern and say, okay, well, that's how medicine is going to work in the future, right? That's certainly how advertising is working today. And so, a lot of times people ask me as a researcher, what does big data mean? This is my example. That it's when you've collected enough data at enough detail to see things that you couldn't see if you had less data. That's the Carrot application. So what we've been doing in terms of building out the badass stack is, we were inspired, like a lot of people, by the Google MapReduce system for doing scalable parallel processing. And what a lot of people did is they said, hey, MapReduce is really good, but it's not really good for what I want to do, right? Because I want to do graph processing, or I want to run database queries, or I want to do real-time processing. And so there was this explosion of new systems developed across the world where people took the basic idea of MapReduce, but then changed it in some way so to solve their particular problem. So they basically specialized it. And the problem with that, of course, is if you as a user want to build a real end-to-end application, you end up having to use all these different systems that were not built together. You often have to copy data from, into one system, process it, write it out, read it into the next system, and so on. So it's very inefficient, and it's incredibly error-prone because all these systems are, open source. They're always changing frequently. So AmpLab took a different approach, and we said, okay, well, rather than specialize MapReduce to solve all these different problems, let's generalize it. Let's make it do more and have a single system that solves a lot of problems. And so it turns out that you really only have to make two basic changes to MapReduce to pull this off. One is you need to be able to do more than map and reduce, right? So you have to have more general processing models. In particular, directed acyclic graphs solves a lot of the problems. So you want to have a richer programming model. And then the second thing is you want to allow the different parts of your computation to share data without having to write it back out to the file system and read it back in. And if you solve those two problems, you can then address all those different use cases we saw before. So what we've done here is we're using Spark as sort of an underlying substrate, and then on top of that, we've built a SQL engine, we've built a streaming engine, we've built a graph analytics engine, we've built a machine learning system. And what's nice about this is then, within that single unifying framework, you can look at the data the way you need to look at it for the particular problem you're trying to solve. You can cobble together all these different modalities, these different ways of working with data, without having to copy from one system to the next. And so this is what we've built in the badass stack. And to our pleasant, I won't say surprise, because that's why we built it, but we're very pleased that a lot of people are finding this to be a very useful way of thinking about big data, and find that the ability to look at the same data set through all these different lenses is a useful and important thing. And so that's a lot of what's driving the adoption of Spark out in the real world. So Spark is sort of at the core of it, And really, what made Spark catch on is we were able to show that for certain important types of applications, it could be a lot faster than Hadoop MapReduce. And I've already told you that we've built the rest of the stack on it. And about 2 years ago, maybe a little less, we donated it to the Apache Foundation, and it's really sort of taken off from that. Now it's called Apache Spark. So just quickly, one of the nice things about doing everything in the open source is we get to expand our developer footprint. So in the current release of Spark, there's over 400 developers. And if you look at sort of activity across open source big data projects, Spark has got a lot more going on than a lot of the other projects. So there's just a lot of enthusiasm and excitement behind Spark right now. It's really all these graphs are showing. So really, in a nutshell, what's interesting about Spark? So before Spark, as I mentioned, MapReduce was sort of the start of a lot of the excitement around big data processing. And the way Hadoop MapReduce works is, if you're trying to build a model or learn a model on a bunch of data, you'd start off with an initial model. You'd have some training data. You'd read it in. You'd run your maps on it. You'd reduce that. You'd collect the results and reduce. You'd learn a model, and you'd have to write that back out to disk. You got a new model, and then you say, OK, well, now I want to improve my model. And so basically, I want to iterate through this process of improving the model, right? Because this is the way a lot of machine learning algorithms work. And Hadoop MapReduce forced you, basically, at each stage to read the data in from disk, do your processing, write it back out to disk, and then when you go to do the next iteration, you'd have to read it in from disk again, maybe to a completely different machine than the previous iteration ran on. And so this caused a lot of inefficiencies. There's all these reads that you're doing for the maps. There's all the writing that you're having to do between stages and then having to read it back in again. And so what we do in Spark is actually pretty kind of obvious once you've seen that that's the problem, is we're going to make much more aggressive and efficient use of memory. So what you do is you read the training data into memory and remember where you've put it, okay? And then you allow the different parts of the computation to communicate not through the disk, which is about the slowest way you can communicate on a computer, but through memory. And when you do this, all of a sudden you get these kind of 10x, 100x speedups for those iterative applications compared to the Hadoop MapReduce type of a platform. And that was sort of the thing that got people excited about Spark when we first released it. OK, the way we're able to do it is through an abstraction we call RDDs, or Resilient Distributed Data Sets. And basically, they're just collections of data that span the cluster. So that's why it works so well for cloud computing. The important thing is that you want to be able to leverage memory but not lose the fault tolerance benefits that you got in a Hadoop MapReduce system. Because when you're running in a big cluster, things can happen. If you're doing a long computation, it's quite likely that a machine or two will fail or somebody will get slow. And so you want to be able to recover these pieces individually. So that's really what the RDD abstraction lets you do, is by having a very narrow interface where you're not allowed to update the RDDs, but what you can do is transform them into new RDDs. You can then very efficiently keep track of all the lineage or the recipe that got you any piece of data in any part of your computation. If you lose that piece of data, it's then very easy to go back and recreate just the part of the data that you've lost. And so that's what RDDs let you do. And as we've discussed, that simple model, this idea of data sets that are spread across the cluster that you're not allowed to change, that you can only transform through this limited alphabet or language of transformations, is powerful enough to represent a bunch of the way people want to process big data. So that's kind of the key insight behind Spark, is this idea of RDDs. If you want to sort of understand this idea of generalization, basically this is a subset of the operators that Spark lets you run on an RDD. So you create a new RDD by applying a map, or by applying a reduce, or by applying any of these other types of functions. So if you're a database person, you'll recognize join and group by and count and things like that. And there's other transformations. So there's a few dozen transformations that you can run on RDDs. OK, so that's what the Spark system lets you do. The current release of Spark is 1.3. It was released last month, and it comes with these features here, the core Spark, the streaming, graph processing, machine learning, and the SQL processor. As we're building in the lab, we're building these other functions, we're making sure that they integrate with the open source version of Spark. So we're not doing a lot of Spark development in the lab anymore, but we're basically, like a lot of other people out in the world, using it as a core component, and then we're building around that. So what I wanted to do, just to focus on the subject of this particular session, is pull out that genomics application that I mentioned briefly already, just to give you a feel for what I think the power of, or the opportunity really is, of bringing kind of modern big data technology to scientific processing. So we've been working on a genomics processing pipeline, and trying to look at how to leverage cloud computing, and this is a big part of our collaboration with Amazon, and these types of Spark-based big data infrastructures that people are using across industries to process big data. And the reason this is important is because genomic data is exploding, right? So the cost of sequencing genomes is going down much, much, much faster than the cost of computing. And there are new initiatives starting up that are going to collect terabytes, petabytes of data by sequencing lots of genomes and then being able to do comparisons across them. And so in order to be able to do this work, you have to be able to run efficiently. And in order to be able to run efficiently, we believe you have to be able to leverage modern hardware and software appropriately. So if you look at the state of the art in genomics processing, or what people typically do, there's a bunch of file formats out there that really aren't meant, they don't play very well with existing or with modern big data technology. A lot of the pipelines are built in a way that there's a lot of hidden dependencies in terms of the ordering of the data and the structuring of data. So if you wanted to take an existing genomics pipeline and change a little piece of it, you could very easily break things because there's some invariant in there that you've now violated that maybe wasn't even documented anywhere. So these pipelines are very brittle. And beyond that, they're just written typically at a very low level, and so there's a productivity hit. And so, if you look at big data technology and you look at database technology, for decades, people have been trying to solve these exact problems, right? So there's the idea of data independence, where you can specify kind of at a logical level what the data needs to look like, but separate out sort of the physical implementation of your actual data structures from the way your applications are written, okay? And this is an incredibly powerful concept, something that's been largely missing from scientific computing until recently. And so what we've done is we said, okay, let's take a step back. We understand a lot about how to do data processing in commercial environments, in a bunch of environments. How do we apply those lessons, like data independence, to scientific computing? So in the genomic space, we've built a system called Atom. And basically, it defines these three things. There's a data schema, so write a logical description of the data, and then a way to lay that data out on disk in a way that you can then exploit cluster and elastic resources. There's a programming interface that lets you do distributed processing, just the way MapReduce or Spark kind of lets you leverage parallel computing. And then there's tools like command line interfaces and other things so that you can have an interactive experience when you're working with the data. Another way to look at Atom is really in this kind of layered stack where at the bottom you sort of have your physical storage and then various data structures. At the top you have your end applications and then the modeling that you do. And where they kind of meet is in the middle is the logical data schema. Okay? So the idea is if you can describe the data logically, you can then leverage lots of developments and improvements at the lower levels in terms of storage formats and in terms of physical data storage. And at the same time, you can innovate at the higher levels for new algorithms. And so it's not a new lesson. It's the way database systems have been developed since the relational model was created. We're just trying to bring that knowledge into the scientific computing realm. And so if you kind of look at what's happening at that middle level, we're using open source tools like Avro to describe the data schema, and then that opens up the whole open source world. So at the lower levels, we're using Parquet to store the data, we're using Spark and Hadoop to process the data, and so on. So the key message here is if you want to get scientific computing moved from sort of the kind of the ad hoc, bespoke, traditional way it's been done into a world where it can leverage all the excitement and the innovation that's happening at big data, we believe that the way to do that is by defining a logical schema the right way. And so that's the approach we took in Atom. You're not supposed to be able to read this, but the bottom line is that the schema is not that complicated. Okay, and again, we use the Avro format, so it's compatible with a lot of different tools out there. And there's some details about how we handle metadata and whatever, but the important thing is it's extensible. Okay, so you define the schema, and then you can extend it as applications change and as the underlying data changes. One level below the schema, we're going to use modern storage formats to actually put the data on disk in a useful way. And so we use Parquet, which is an Apache incubator project based on Google Dremel. And what it does is it's a format for doing highly performant and compressed columnar storage. It lets you push predicates down into the file system so you don't have to read all the data every time you want to find something. And this has benefits like benefits of compression, benefits of faster access. But more importantly than that, by separating the logical schema from this physical implementation, you don't have to worry about things like sort order and dependencies from one stage of your processing to the next, because that all works out at these lower levels of the system. Okay? And so this is kind of the key to making it work. I'm going to skip that just right to what this lets you do. So this is a bit of an eye chart, and I apologize, but at the top, we ran sort of the traditional, what's called a GATK genomics pipeline, where from the beginning to the end, it takes, in this particular case, about 2,075 minutes. So you have to do the math on that in terms of how many hours that is, to run on a single node. With our system Atom, we can run on a single node at about the same speed. These are old results. I'll show you some in a second. They're a little better than this. But we can run at about the same speed on a single node. But then, because we're using these modern data formats and these modern tools, we can start spreading out across the cluster and across the cloud. And so you can run with 32 machines, 64 machines, 128 machines. And what you can see is we can get that time down from 2,100 hours down to about, 2,100 minutes down to about a little over an hour, okay? And the cost on Amazon at the time we ran the experiments was about a third, okay? So there's not a lot of magic going on here. It's just saying let's not use the old file formats that kind of constrain us into doing single node processing. Let's open up to the modern big data world and then take advantage of scale-out processing like everybody else is doing with big data, and then you get the advantage of that type of scale-out processing. Okay, and so that's really the lesson here. This is a more recent result that shows we can actually run on a single node faster than this GATK platform. And then, we're for the various phases of the processing, and most of them we're getting sort of linear scalability up to 128 nodes. And we have a little work to do on some of them. Okay, so just to wrap up, the Atom project is one part of what we're doing in AmpLab. We're building an entire, top to bottom stack for big data processing. And the key message for scientific computing is that if you want to use, our stack or a stack like it, you really want to start thinking about what's the logical schema of your data. Use some of the lessons that people have learned the hard way over data management over decades of separating logical data design from the physical data design to, from the applications that you're actually running. And what we're now doing in our project is we're kind of moving up the stack. And so we're looking at how do we make it easier to build these analytics applications? How do we make machine learning easier? How do we automate a lot of the process of choosing parameter settings for different algorithms, for choosing which algorithm to use to do a certain analysis, and so on. And so if you keep an eye on what we're doing at the AMP Lab, you'll see some of those new systems coming out. And so that's really all I have to say. If you're interested in what we're doing, there's the place to find us. But with that, I think Jamie's going to come up and we'll take some questions. Thank you.
Thanks, Mike. So I'm just going to point you to a couple of additional resources. So if you'd like to learn more about high-performance computing on Amazon, big data, genomics, compliance, security, we have pages that make it easy to find these. You want to stay up here, Mike?
Okay.
Okay. But now we'd like to end the presentation and switch over to questions. And so, but before we take the first question, I just want to remind you that we're eagerly seeking your feedback on this presentation. So if you could take some time and just complete the survey and let us know what you thought of the presentation, we'll read any of those comments. But at this point, if you have questions about Psycho, about badass technologies, the floor is yours. Yes?
Great presentation, thank you. So, two-part question. One, will Atom eventually plug into like the Global Genomics Alliance and kind of the Beacon project and those other overarching data management strategies? And then two, will this project become a bolt-on to kind of Cloudera's genomics platform someday, be monetized? We worry about that.
Okay.
If you'd repeat the question.
Sure. So there's a twofold question. One is Atom going to be part of some of these bigger initiatives like the Global Genomics Alliance? So I'll answer that one first. So the main people from our lab who were involved in creating Atom were also involved in the creation of the Genome Alliance. And so we're trying to be involved, would love to be involved, and those conversations are ongoing. The second part of the question was, what about relationships with Cloudera's genomics, in particular Cloudera's genomics efforts? And I'm not aware of any conversations going on specifically with Cloudera, but I will say the AMP Lab has been doing everything in the open source, and so a lot of our software has been picked up by Cloudera and many of the other big data vendors, and so it's quite possible that some of this stuff might end up there. Certainly, I think the philosophy that we've had in terms of how to move scientific computing into this bigger framework of big data processing, I think a lot of people will be doing that.
Yeah, I'll just add to that a little bit. So Amazon, actually at the invitation of the AMP Lab, really got involved very early on with the Global Alliance for Genomics and Health, GA4GH. And we have several members of AWS that are active participants on normalizing or trying to come up with more consistent health policies, genomics, privacy policies around the world, to develop better tools and APIs for exchanging information and doing analysis across multiple large-scale repositories of genomic data, and publishing technical and economic benchmarks on various approaches that you might use, so that we can come up with the best techniques for analyzing this data at scale, so that we can get to those fantastic outcomes. And so this is it's very important, I think, to both of our organizations. Yes. Any other questions? Yes. No, I wish we could take credit for that. So the question is, was it Amazon who was responsible for the discovery of the Higgs boson? No, that wasn't us. But the teams the CMS and the Atlas particle detectors, and the collaborations of several thousand researchers behind each of those that found the Higgs boson, have been using AWS to do some of the simulations and analysis leading up to the first of the long shutdowns. Now that LHC, the Large Hadron Collider, is back online, they're focusing on questions related to supersymmetry, dark matter, dark energy, and finding some particles at higher energies. And Amazon will play a very significant role in the compute and data analysis behind those discoveries. But the science, that's members of a very large global community of high energy physicists. Thanks.